Hi, so welcome. This is our 19th exploration. So this is our 19th exploration of Sylow's theorem. 19th exploration of Sylow's theorem. Okay, again we need to turn down the music. Alright. Alright, cool. So Sylow's theorem is really telling us the following, that if the order of G equals to P to the alpha times M, and P and M are relatively prime, then it must be the case that there exists some subgroup H of G such that order of H equals to P to the alpha. Right. This is the claim, but at the moment we're not sure whether it's true, and we've been trying for quite some time now to prove the statement. So we've made some progress. For instance, we seem to have concluded that if G is cyclic, then clearly there's a subgroup of order P to the alpha. And so the case seems to be trying to prove to see what happens when G is not cyclic. So for instance, if you can prove that if G is not cyclic and order of G still equals to P to the alpha times M, well, if we can prove that there's also always a subgroup H of G such that order of H equals to P to the alpha, it seems like we'll also be done in that situation. But the challenge still remains, how do we deal with the case when G is not cyclic, and why are we necessarily guaranteed a subgroup of order P to the alpha? So before we came upon this idea, now we don't know if it will pan out, but let's check first. The idea was, what if we could prove the following, that there is actually some, let's look at a special case, that is when order of G equals to P squared. Okay, let's write it well. So suppose that order of G actually equals to P squared, right, times some M, okay? Then, and let's assume that we've actually found some subgroup L of G such that order of L equals to P, right? Not necessarily P squared, but equal to P. Can we use this information to somehow conclude that the reason we're doing this is it appears that if you can show that there is a subgroup of order P, if you can show that the existence of a subgroup of order P implies the existence of a subgroup of order P squared, then maybe we can extend that idea to P to the alpha. That's kind of the main picture here. But let's see if this works. Suppose we can actually find a subgroup of order P. Again, we don't know if this is true, but suppose we can find a subgroup of order P. Then now consider the group L cross L. Right? Well, what's the order of L cross L? Isn't the order of L cross L just the same as order of L times order of L? Right? What does that equal? Is an order of L equal to P? So are we saying that the order of L cross L is really equal to P squared? Okay. Well, we're not right. Is L cross L a subgroup of G? Well, if L is a bunch of ordered pairs, how can L cross L be a subgroup of G? Right? They don't even seem to be the same type of object. L cross L is some ordered pair, and G is just some elements. Okay. They may or may not be, is what we're saying. So actually, even if G was a bunch of ordered pairs, now we would have ordered pairs where every element is an ordered pair. Okay. So L cross L is fundamentally appears to be a different type of object than G. Right? But perhaps we can say the following. Perhaps we can say that while L cross L is not necessarily a subgroup of G, perhaps L cross L is isomorphic to some K, which is a subgroup of G. Right? Now notice that if we can establish this, if we can establish that L cross L is isomorphic to some subgroup of G, then won't we be saying the following, that the order of L cross L equals to the order of K? Right? Okay? So, but still, the challenge remains. And what's the order of L cross L? Didn't we say that the order of L cross L was P squared? But if the order of L cross L is equal to the order of K, then aren't we saying that we found some subgroup K of G whose order is also P squared, right? A subgroup of G whose order is P squared. So, ultimately the challenge lies in, well, we have a bunch of question marks, obviously. Let's not forget. One is, well, why can we assume that there's a subgroup of order P? And the second question is, suppose we actually have assumed that there's a subgroup of order P. How do we know that we can find an isomorphism between L cross L and some subgroup K of G? How do we know that we can do this, right? So, well, how do we know that we can do something? Perhaps we can present a way to show that we can do it. That is, perhaps can we actually think of an isomorphism between L cross L and K, where K is some subgroup of G, right? Well, what would an isomorphism look like is the question, right? So this might help us to decide whether there is actually an isomorphism between L cross L and some subgroup of G. So what do the elements of L cross L look like? And they elements of the form phi of, let's say, what, L1, L2, right? An ordered pair L1, L2, where okay, where is this? Okay, so we have L1, L2, where, well, what can we say here? Can we say that at least, well, I mean, what are we saying about L1? Are we saying that L1 and L2 are both elements of G? Okay. Actually, you know, not just G, they're elements of L, subgroup of G. Okay. So, well, where would we have to send L1 and L2 to guarantee that what we have ourselves an isomorphism? That's the question. Um, we tried sending L1, L2 to L1 star L2, and that turned out to not necessarily be fruitful. And so, which begs the question, well, where else can we send L1, L2 to guarantee that we have ourselves an isomorphism here? Um, Remember, when kind of make sure that it's injective and surjective. Well, one idea might be to send it to the inverse of something. L1 maybe L2 inverse, right? Um, I wonder if this works. Well, let's see. Is it even an isomorphism? What is what is phi of, for it to be an isomorphism? What would we have to check? Wouldn't we have to check that at least it's first a homomorphism? That is phi of L1 L2 multiplied by L1 prime L2 prime is really the same as phi of L1 L2 times phi of L1 prime L2 prime. Right? Isn't that what we need to check? Okay. So let's see, what does the left hand side give us? What's L1 L2 times L1 prime L2 prime? Isn't that the same thing as L1 prime L2 L2 prime? Okay. What's phi of that then? So what's if phi if the product of L1 L2 and L1 prime L2 prime is this, is the same as L1 L1 prime comma L2 L2 prime, then isn't phi of the product just the same as saying phi of L1 L1 prime times L2 L2 prime? Okay. But what does that equal to? Alright, so I forgot to set the timer. Alright, I'm gonna make that an extra 14. Alright, so this is what we're looking at now. Well, L1 times L1 prime. Well, what does that give us? Well, I mean, by our formula before, we're saying that this is the same as L1 times L2 inverse, right? So the first thing times the last thing inverse. So isn't this going to give us L1 times L1 prime multiplied by L2 times L2 prime inverse? Okay, well, what's that equal to? Is that the same as L1 prime perhaps times L2 prime inverse times L2 inverse? Okay, so this appears to be the left hand side. What's the right hand side going to give us? Well, what's phi of L1 L2? Well, isn't that the same as L1 L2 inverse? What about L1 prime L2 prime? Isn't that the same as L1 prime L2 inverse? So are we saying that the right hand side phi of L1 L2 times phi of L1 prime? Okay, let's write this clearly. Are we saying this, that times phi of L1 prime L2 prime? Are we saying that all of this actually equals to L1 L2 inverse times L1 prime L2 prime inverse? Okay, well, is so then are these things the same? Is phi of L1 L1 prime times L2 prime the same as phi of L1 L2 times phi of L1 prime L2 prime, right? Do they look the same to you? Okay, right, but perhaps not. Sure, L1 and L1 appear to be the same. L2 inverse, sure, but yeah, here we have L2 prime inverse. It's unclear. It's unclear how this is going to work. Yeah, they're again mixed up. So the basic idea is that if this phi from L cross L to K is not even a homomorphism, how can it possibly be an isomorphism? So again, a nice try here, multiplying L1 by L2 prime, L2 inverse, but that's not helping us either. So question, is there some other isomorphism we can define from, is there some isomorphism, not some other, is there some isomorphism we can define from L1, L2 to uh, some element, some subgroup of K, basically? Is there some isomorphism? We've tried multiplying stuff out and taking inverses, and that doesn't seem to work. Um, Maybe we can think about what was stopping our previous examples from working here. What would we need to do in order for them to be pretty much the same? Um, well, the projection map is a homomorphism. The only thing is the projection map. That would, it will take L1, L2 and just give us L1 back. So the only thing is that it's not necessarily injective, right? So because I mean, if phi of L1 L2 is L1, we also have that phi of let's say L1 times some other element L2 prime is still going to equal to L1. So so this is kind of like a projection, you can think of it. That's, they usually call it a projection, but still, even this, it's not even injective. We have two different elements, L1, L2, L1, L2 prime, giving us the same element. So if a function is not injective, how can it be an isomorphism? So again, just setting it equal to L1 or L2 doesn't seem to work either. Um, okay, let's try one more here. Um, you know, this, how could we have made this thing work? Is there anything we could have done? Let's say we're to manipulate L1, L2 inverse times L1 prime, L2 prime inverse. Suppose we're to manipulate this in order to obtain that, in order to obtain this. What would we need to do in order for them to be equal? Well, obviously, a thing is if L were a billion, right? If L were a billion, then we would be good. Oh, actually, ooh, wait a second. Dude, dude. Okay, okay, okay. Alright, so, oh, actually, don't we have ourselves a problem here? Think about it. So, okay, we've taken, yeah, maybe we can figure out a way to dispose of this approach. We've taken some L subgroup of G. We've said that the order of L equals to P. If the order of L equals to P, doesn't that mean that L is cyclic? Okay, if L is cyclic, doesn't that mean that L is a billion? So, okay, L is a billion, all right? Okay, isn't a cyclic group just a billion? Think about it. If L is cyclic, it means there's some little L that generates big L, right? So aren't we saying that L is of the form L to the 0, L to the 1, L to the 2, blah blah blah, up to L to the P minus 1? Well, isn't this group cyclic, right? Isn't L to the I times L to the J the same as L to the J times L to the I? Alright, so if this is true, then, alright, so we're saying L is a billion, alright? And now we're trying to create a homomorphism, phi, from L cross L, sorry, an isomorphism phi from L cross L to some K subgroup of G, right? And before we're trying a bunch of approaches which involved multiplying elements of L cross L. So before, what we tried was this. We said, okay, well, why not just get, let's say, L1, L2 and send that to L1, L2 inverse, right? But notice that if we consider all values of L1 and multiply every possible L1 by L2 inverse, eventually isn't the image, right? So, okay, maybe it's not as much the image, but all right. Let's give it another shot. Let's not be too pessimistic. So now let's consider what we've been looking at before. Well, we said that if we set L1 to L2 inverse, okay, where did we write these things again? Okay, here, right. So notice that if L is a billion, right? If L is a billion, then so things commute, right? So if commutativity is allowed, then can't we just shuffle these things around? So for instance, L1 will have L1. L1 we could just move L2 inverse over there, and then we have L1 prime, just move L1 prime. Basically, if the group is a billion, if L is a billion, do you agree that that would imply that phi of L1 L1 prime times L2 L2 prime is the same as phi of L1 L2 times phi of L1 prime L2 prime? Right? So let's see if the two if L is abelian and we're just saying that it is because it has prime order, then don't we at least know that, well, if we define phi as L1 times L2 inverse, well, that's just going to give us the entire group back, right? So, sorry, it's not going to give us the entire group back, but it's going to guarantee the following, that indeed, right, this statement, that phi of L1 L2 times L1 prime L2 prime is the same as phi of L1 L2 times phi of L1 prime L2 prime. Right? So what does that mean? At least phi is a homomorphism. Okay. So we found ourselves a homomorphism, but that's not enough, is it? Didn't we need to prove that there is actually an isomorphism, right? So not just an homomorphism, but there's an isomorphism between from phi to some subgroup of G, right? From L cross L to some subgroup K of G. Okay. So at least we know that phi is a homomorphism, but is it injective? That is, right, is it, right? Phi is a homomorphism, cool. Phi is homo, right? But is phi injective? Is a question, right? Let's check that. Is phi injective? So how would we check that? Well, one method seems to be to check that the kernel of phi actually equals to the identity element, which for the group G isn't that just the element 1? Okay, well, let's see if that's true. Um, what's if we define phi of L1 L2 to equal to L1 times L2 inverse, right? Well, that's phi of L1 L2, right? Phi of L1 L2 to equal to L1 times L2 inverse. Well, how many ordered pairs L1 L2 are gonna give us the identity, right? Okay. And does it make clear that there are at least p of them, right? Isn't that right? So, for instance, if we got the group L and wrote it like this, L1, L2, all the way up till L times p minus 1, right? Can't we say that, well, phi of L1 times phi of L1 times L1, phi of L1 L1, right? What's that going to give us? Isn't that the same as L1 times L1 inverse? But what's L1 times L1 inverse? Isn't that the identity? How about just for any element of our group here, for any L sub j, L sub j, isn't this still going to give us L sub j times L sub j inverse, which is again the identity, right? So question, is the kernel of phi just going to be the identity element? Isn't how many elements are there? Aren't there more than aren't there p elements? Right? Aren't there p ordered pairs which are going to give us the identity when we apply phi to them, right? So so can we conclude the following, that kernel of phi does not equal to the identity? If kernel of phi does not equal to the identity, well, how can phi be injective, right? So if phi is not injective, how can phi be an isomorphism, right? So again, this was perhaps a good try, but either way, it's not helping us to gain an isomorphism between L cross L and a subgroup of G. All right, so we run out of time, so let's just take a short break and yeah, see you on the next video. We'll continue from here, maybe figuring out if we can, what techniques we have for defining another type of isomorphism. All right, thanks a lot and have a relentless week.